Physicists may have made a huge mistake when they introduced dark energy. This is what a team of mathematicians say after looking at the equations, because they find that actually dark energies are necessary. If they're right, that'd be the ultimate embarrassment for physicists. Let's have a look. About 25 years ago, astrophysicists noticed that the universe does not just expand, the expansion is getting faster too. This doesn't sound like a big difference, okay, so we thought the universe expands, now the expansion also changes in time? That can't be so difficult to include into the equations, and indeed, it's not difficult to include mathematically. The problem is entirely on the physical side. To get the expansion to accelerate, you need a peculiar sort of energy with negative pressure. There's no such energy that we know of, so physicists just postulated that it exists and called it dark energy. The authors of the new paper now say that this extra ingredient was never needed. The expansion of the universe speeds up simply because Einstein's equations do that anyway. This would be amazing because dark energy has become a big expanding headache, and the headache's expansion seems to be speeding up as well. You see, dark energy, if it exists, is not a small contribution to the universe. It'd have to make up most of the energy, more than 3/4. Despite that, we supposedly can't measure it anywhere on Earth. It just sits there doing nothing. We also don't know what, if anything, it's made of. And in the past years, it's become clear that the simple idea that dark energy is just a constant contribution doesn't quite work. We now have multiple sets of data that require dark energy to change in time, and astrophysicists are busy cooking up reasons that in hindsight explain why it actually has to be this way. The authors of the new paper say that physicists have simply screwed up the mathematics. You see, physicists usually assume that dark energy is just there since the beginning of the universe. This team of mathematicians instead asks, okay, but what if it's not there? Instead, they look at the first moments of the universe without dark energy. They just put matter into the universe, not perfectly smooth, but with small deviations from this smooth distribution. Over time, gravity will make the matter clump, which creates stars and later galaxies. The presence of dark matter alone makes the universe expand, we know this, but it doesn't make the expansion accelerate. This is the usual problem. But the mathematicians find that the case in which the universe expands evenly due to the presence of matter is unstable. It's a mathematically ideal case that doesn't make physical sense. In reality, they say such a matter-filled universe would not expand evenly. It'd fall apart into regions with different expansion rates. In some regions, the expansion accelerates. So they say we live in one of those regions where the expansion happens to accelerate, and that's it. No dark energy necessary. The reason they get a different result from what astrophysicists normally get is that they remove one important assumption, which is that the universe is on average the same everywhere. It's called the cosmological principle. The interesting thing about the paper is that their mathematical treatment is totally different from what physicists usually do. They use a formalism that lets them study the stable and unstable configurations and the attractors of the entire system. The general idea that physicists have oversimplified their description of the universe and caused themselves problems that don't exist is not new. What's different about these mathematicians' analysis is that they found a way to prove that the cosmological principle is physically highly questionable. It's like the example of a pencil balanced on its tip. It exists only in Plato's ideal world of mathematics. That all sounds intriguing, and I do think it's a nice paper, but this is a paper from mathematicians. They derive equations, and this is all well and good, but they don't check whether the results of their calculations agree with the observations. And that's a high demand. Their idea would have to fit all the cosmological data: supernovae, the cosmic microwave background, baryonic acoustic oscillations, lensing, structure formation, etc. The currently used standard model of cosmology, the one with dark energy, is not popular because cosmologists enjoy mysterious ingredients. Well, only because of that. It's popular because despite its shortcomings, it fits a lot of data. This is why I give the paper a 6 out of 10 on the bullshit meter. Nice maths, not much physics. So for now, dark energy remains in the model, mostly because it fits the data and partly because cosmologists have already printed the conference posters. For more than half a century, people who've been taking the psychedelic drug DMT have reported encounters with alien beings. These aliens often act as guides, teachers, or messengers. Now a scientist says, well, maybe these beings are real and psychedelics are just a way to open human perception to their presence. Not only this, he says he's got the mathematics to back up his idea. And it's testable too. Well, wow, forget about string theory and extra dimensions. Here come aliens and psychedelics. Let's have a look. DMT is short for dimethyltryptamine, a fast-acting and strong drug that causes hallucinations. Smoked, it hits in seconds, lasts about 10 minutes, and people rarely stay alone. In a sample of more than 3,000 trip reports, conscious entities show up in 45%, and the cast is oddly specific. 24% meet a feminine being, 17% a deity, 16% an alien, and 8% a machine elf. For about a century, neuroscientists called it hallucinations, but cognitive scientist Donald Hoffman and collaborators say we've been too quick. In a new paper titled Traces of the Other, they argue these beings might be real. Not only this, they say it's a new science of reality, where consciousness, not matter, is fundamental. I'll do my best to try and take this seriously, because the people behind it are not obviously cranks, but it's a perfect example of a problem I worry about a lot. What happens when scientists mistake maths for reality? That said, the general idea behind the alien hallucination paper goes back all the way to Kant. We don't perceive reality as it is, only a useful version of it. Hoffman popularized the modern form of this in his 2019 book, The Case Against Reality. The example he likes to use is icons on a desktop. The trash icon isn't really the circuitry inside the computer. It's just useful to pretend you're deleting your files before remembering you didn't mean to delete them. Our senses, Hoffman says, work the same way because evolution rewards survival, not truth. That part, I think, is fairly uncontroversial. Critics mostly say it's nothing new, just old ideas and fresh language, but Hoffman then goes beyond that. If perception is just an interface, he asks, what's behind it? And his answer is nothing. Conscious agents are the only thing that exists. Reality is just that, a network of interacting minds, and we only ever see a thin slice of that interacting network of minds, so there could be countless other minds out there that we don't know of. In the new paper, they therefore suggest, quote, some DMT entities might correspond to traces of conscious agents that are normally imperceptible. And they have maths. Kind of. In their paper, a mind is a symbol for a probabilistic map. This means it's a maths thing which takes one state, your reading of a menu, say, and gives you probabilities for the next state. For example, you picking chicken. Mathematicians call it a Markov kernel. It's used for things like weather forecasts and stock prices and really standard maths. And that is the problem. Nothing in those kernels encodes anything to do with consciousness or experience. It's a label they tack on by hand. In integrated information theory, at least they try to calculate consciousness from a system's physical structure. It doesn't really work, but hey, at least they're trying. In Hoffman's work, consciousness is just a word for maths that could as well describe a stock portfolio. As Pauli said, it's not even wrong. There's nothing there to be wrong. But fine, who cares about philosophy if there's experiments? They propose several ones. For example, people on a DMT trip might be able to see colors on a screen in a different room because their alien is there. Or different people might share the same alien presence. And this is all well and good. The problem is they're not going to see this. And then they can say, okay, but actually the alien didn't feel like helping out. Or actually the aliens have a different notion of space or whatever. Not even wrong, as you see. You saw it coming. It's a 10 out of 10 on the bullshit meter. It's fancy words decorated with useless maths. But it's not all nonsense. There's something genuinely strange going on here. Dreams and psychosis recycle the familiar. People you know, places you've been, things you've seen on YouTube and wish you hadn't. DMT serves up aliens. Why? Nobody knows. In conclusion, the phenomenon is real and worth studying, but the maths is nonsense, and I'm sorry to report there's no evidence of alien consciousnesses attempting to communicate through psychedelics. Wow, that was quite a trip. This new lawsuit could change the course of science. I know that title sounds unbelievable, but hear me out. A federal judge in the US has allowed a lawsuit to continue on which a former official of the NIH, that's the National Institute of Health, David Zielinski, sues one of his former colleagues, Lee Nadler, at Harvard. The spicy part is the reason for the lawsuit. It's that Nadler allegedly repurposed NIH grants and falsely said he'd met objectives. Zielinski claims that Nadler bragged to colleagues about first applying for grants for his research center and then deciding what to do with the money. The reason this lawsuit could hit big is that this happens all the time. You see, the NIH and the NSF and a lot of national funding agencies globally have official rules that you must comply with, but everyone in academia knows their lip confessions, and most of what they write in the grant proposals is bullshit. You need timetables with milestones to be checked off and a statement of relevance for just exactly how your amazing research will benefit your country and so on. So they make up timetables and milestones and some reasons for why yet another nonsense solution to the black hole information pseudo problem will benefit the nation. I don't know whether the person who's being sued really bragged about basically lying in his grant proposals, but if he did it, it wouldn't remotely surprise me because I've had faculty members do the same thing. In academia, it's become entirely normalized. You don't have to take my word for it. Anonymous interviews among academics in Great Britain and Australia have also demonstrated that lies and exaggerations have become routine in proposal writing. Participants of the study refer to their impact statements as charades or made-up stories. This is not the first time that an NIH grant recipient got sued. There have been a handful of cases in the past years, but the earlier ones, like those at Duke and Cleveland Clinic, were more obviously fraudulent and concerned data falsification, image manipulation, or false affiliations. The new lawsuit instead tackles a money repurposing tactic that's extremely widespread in academia, not just in the United States and not just in the life sciences. What makes this case particularly interesting is the question it raises. How did this go on for over a decade without NIH catching it? The most obvious explanation is that NIH knew, or at least strongly suspected, what was happening but didn't care because this kind of flexible and often misleading grant management is widespread and tacitly accepted. Indeed, according to the Harvard Crimson, the university had tried to prevent the lawsuit because the court should be skeptical that the NIH somehow missed that 2/3 of the work contemplated was never done. Yes, exactly. How could the NIH have possibly missed this? The obvious answer is that they didn't miss it. They didn't care. You may wonder why Zielinski would even sue Nadler if he's potentially shooting the NIH into the foot. That, at least, is not difficult to guess, because this is what's called a cui tam lawsuit under the American False Claims Act. The whistleblower, in this case Zielinski, sues on behalf of the US government. If he wins, he gets 25% of the money he saved the government. It's hard to say just exactly how much this is, but the NIH grants for the Harvard Catalyst under Nadler's guidance totaled more than $200 million. So if Zielinski wins, he'll have a very cozy retirement, and there'll likely be more such lawsuits. Now look, I'm not claiming that everyone in academia is a fraud, and indeed one may ask whether fraud is a good term for lies that have become so normalized. They're simply necessary to survive in the system. If they were honest and declared that actually their research is irrelevant and a waste of money, they might as well not submit the proposal in the first place. The entire process is not one that rewards honesty. And the problem has a flip side, which is that researchers who want to try something conceptually new face such a high risk of rejection that they don't try in the first place. There have been many initiatives to overcome this problem. The most recent one is the NSFX program from the American National Science Foundation that is, quote, designed to launch and scale a new generation of organizations focused on independent research, development, and innovation. This initiative will fail for the same reason as all previous initiatives in all other countries, because they'll ultimately draw on the same pool of reviewers as everyone else, and they'll just reinforce the same standards again. You can't escape the committee by appointing a committee to escape committees. This is a problem that AI could actually help to mitigate, but there doesn't seem to be much effort into this, which is interesting in its own right, isn't it? In summary, academia may soon discover a new incentive structure. It's called consequences. Scientists have figured out how to make anti-gravity. Sounds crazy, yet I think it might actually work. But before you go and buy ceiling furniture, let's have a look at the ifs and buts. In Einstein's theory of general relativity, gravity is always attractive. The reason is quite simple. In gravity, energy plays the role that electric charges play in electromagnetism. It's just that since gravity is mediated by a spin-2 field, like charges attract and unlike charges repel. And since there are only positive masses and only positive energies, they all attract each other. But according to the new paper, quantum mechanics offers a loophole. Under the right conditions, two attractive gravitational pulls can combine into an effective repulsion. That's a stunning conclusion they arrived at by studying an entirely different question, namely how to find out whether gravity itself is quantum. This is one of the biggest unsolved problems in physics. We have quantum mechanics, which describes atoms and elementary particles through quantum fields, and we have general relativity, which describes gravity as the curvature of space-time. Both theories work extremely well. Unfortunately, they don't fit together. It's like having two instruction manuals for the universe, one that says assemble with screws and the other says there are no screws. And then a theorist walks in and says, have you tried 11 dimensions? For a long time, most people thought that testing quantum gravity would require absurdly high energies, like inside of black holes or at the Big Bang. But in recent years, physicists have finally realized that it's possible to test quantum gravity in the laboratory. The currently most discussed idea is to use what's called an entanglement witness. That's if you create entanglement using only the gravitational interaction. If this is possible, then you can conclude that gravity must also have had quantum properties. It's a difficult test because for this you have to put massive objects into a quantum superposition. They have to be massive enough so that the gravitational interaction has a measurable effect. The problem is that the quantum properties of massive objects go away very quickly. This is why we don't normally see people being in two places at once. It's also why the experiment has not yet been done. The authors of the new paper now suggest a slightly different route. Their proposal is to use one massive object, the source, in a superposition of two places, and nearby is another particle, the probe. The source mass is put into two possible locations at once. The probe then feels gravity from both possible locations of the source. If the source were in just the first place, the probe would be attracted towards that. If the source were in the other place, the probe would also be attracted just towards this different place. The twist is that if you have the source in two places at once, you can create a destructive interference that leads to a net repulsion. Wait, what? Doesn't this violate some sort of conservation law? No, it's fine, really. If you average over many runs of the experiment, you get what you expect, namely that the probe particle is attracted to the average of the source particle. But in single runs, you can get this repulsive effect. It looks like gravity became repulsive, but really it happens because quantum particles are not just particles, they're also waves, and waves can interfere. If you have a particle in two places at once, then the particle has not one particular momentum, but many different ones. And if these add up in a weird way, the result can push away rather than, as you would expect, make a pull. It's not a new fundamental force, it's an effective force that only occurs for specially prepared quantum states. But that's exactly why it's interesting. If the gravitational interaction didn't have quantum properties, it could not produce this effect. If the wrong way kick is observed and all ordinary forces are ruled out, it'd be evidence that gravity has quantum properties. That said, the experiment is still hard because the gravitational interaction between small objects is ridiculously weak. The authors make an estimate with cesium atoms as the probe particles and find that the source mass would have to be about 20 micrograms. That's about 2 million times larger than what current technology allows, though the masses might go down if either A, the decoherence time increases, B, force measurements become more accurate, or C, shorter distances can be resolved. So, no, you can't yet float to work, but given the current state of public transport, I understand why you ask. I give this paper a 2 out of 10 on the bullshit meter. I have misgivings about this sort of experiment in general because even if the effect is observed, I think it'll be extremely difficult to rule out it was some other interaction. And if it isn't observed, the result is inconclusive because that wouldn't mean gravity has no quantum properties. It'd just mean it doesn't have these particular quantum properties. Still, I have to say that this is a neat contribution to the literature, and I hope the question of repulsive gravity will receive more attention. And if this works, I finally have a scientific excuse for why my hair does not obey gravity. Thanks for watching. See you tomorrow.